we will continue our discussion on stereogeometry, and we discussed the concepts related in this geometry like epipoles, epipolar lines, epipolar planes, then the fundamental matrix and how fundamental matrix converts an image point to an epipolar line in the other plane where the corresponding image point lies. We also discussed about the fundamental matrix of calibrated camera setup when this matrix is called essential matrix. Now, in this lecture we will further elaborate the parameters or elaborate the properties of this essential matrix. So, it is in brief it can be called as stereogeometry for calibrated cameras. So, in this case we represent say the projection matrix is K I 0. So, since I know the calibration matrix, I can convert it into a canonical form of I 0, and also the other matrix I can also convert it in its canonical form, because just by applying rotation and translation parameter itself, all the image coordinates are represented in normalized image coordinate system. So, I can also convert it as R transpose, R and T. So, this is how in the canonical form the coordinates can be converted just by multiplying with the inverse of the calibration matrix. So, you see that in the first camera x is converted to x c, which is the coordinate in the canonical setup of pinhole camera. Similarly, x prime is converted to x c prime by applying the inverses of their respective calibration matrix. So, this is what the expression. So, now if I consider if I apply the relationships of fundamental matrix in this setup, then that fundamental matrix is called essential matrix or E, but the relationship remains the same. So, it is x c prime transpose E x c, that is equal to 0. You note that in general it is x prime transpose f x equals 0 when we do not have any idea of k and k prime from the projection matrix. So, how a uncalibrated fundamental matrix, that means fundamental matrix for uncalibrated stereo setup is related to a calibrated stereo setup. So, how they are related? So, their relationships can be expressed using those calibration matrices itself. As you can see with this simple derivation that x prime transpose f x equals 0, then convert x prime transpose into its canonical form as k prime x c transpose, similarly k x c, and then you consider the middle part of this composite matrix. So, that is a 3 cross 3 matrix. So, this matrix is nothing but this is the essential matrix E. So, this is what is E. So, the relationship between fundamental matrix and essential matrix can be expressed with using these calibration matrices as k prime transpose f k. K prime is the calibration matrix of the second camera and k is the calibration matrix of the first camera. Similarly, you can also get fundamental matrix from essential matrix by using those calibration matrices. So, the calibration matrix, it reduces into this form, because if I consider once again, you note that relationship, if you remember it, suppose I have I 0 and then R t, say these are the two camera matrices, this is P and this is P prime. So, if you remember that this structure was M small m in general, and the fundamental matrix was given as this M cross matrix, which is a skew symmetric matrix, into M. So, that is how the fundamental matrix can be derived. So, in this particular setup, using the same relationship, I can write E as this T cross into R. So, this is how the essential matrix can be represented or can be derived. So, I will replace that value. So, here you note that there are only 6 parameters involved in this particular operations, like 3 parameters related to the translation of camera center, that is the translation parameters, and rotation of the orientations, rotation of the axis. So, that is also 3. So, there are 6 parameters which which are involved in constructing the essential matrix. And since scale is involved also, that means if I multiply essential matrix with a scale value k, still all this relation holds. So, out of them once again 5 are independent, and also the epipoles in its canonical representation. So, it also has those relationships holds, that means E E C should be this, or E C prime E, this is what is there. This is a right 0 and this is a left 0. It is a E C prime transpose E, which is missing here. There should be a transpose here, because it is a right 0, but you have to take it a transpose operation, and its rank is also 2 like F. So, determinant of E should be equal to 0, and as I mentioned, degree of freedom of E would be 5, because a scale factor is associated with E and it has 6 parameters. So, it should be 5. Now, consider a situation of special kind of stereo setup, where you have pure translation of camera centers, pure in the sense that there is no rotation of axis. So, in that case we can very easily express the projection matrices, I mean very simple, in a simple structure, like if you have pure translation, then projection matrices can be expressed as, say, k I 0, I am representing again in the uncalibrated form, then p prime is k prime I t. So, simple translation. So, k prime t is that translation of the camera. So, your fundamental matrix is expressed in this particular setup is in this form, E prime cross k prime I k inverse. You remember that I is actually, if it is in general case, it should be rotation matrix R. So, in this case rotation matrix itself is an identity matrix, because there is no rotation, and then this can be reduced as E prime cross k prime k inverse. That is the structure of fundamental matrix. And if I consider both the calibration matrices are same, which means they are the same camera, they are it's the same camera is taking the images, or it has been fabricated in such way that all other intrinsic parameters, they remain the same. So, then fundamental matrix takes a very simple form of E prime cross only. So, just from the epipole, you can right epipole, you can compute the fundamental matrix itself, whereas E prime cross is given in this form. We discussed why this form is there. I mean, this is the definition of E prime cross, and since you have, if you consider a special kind of translation that it is a parallel to x axis, then E prime is the vanishing point of x axis, and which is given by 1 0 0. That is the intersection. So, the intersection of that point, and so this matrix, fundamental matrix, it has a structure like this. So, only 2 non-zero elements, and the structure is very simple. So, if I apply this relationship of corresponding points, then we can show that the y coordinates actually they remain the same. So, in this representation, there we need to highlight few things, that x prime here is a vector. So, x prime is, it is a vector, and in my representation we consider for example, these points are say x prime, y prime, 1. So, please note that just this is a vector, these are the scalar values, and x is given by x, y, 1. So, now if I apply x prime transpose, which is x prime, y prime, 1, into f, which is given by this 0 0 0 0 0 minus 1 0 1 0, and then x y 1. If I perform this computation, so we can say, we can reduce this computation as say x prime y prime 1, and then as you can see, the first part would be 0, next part would be minus y, next part would be 1, next part would be minus 1, and this is y. So, that is equal to 0. So, once again if I multiply it, it is minus y prime plus y equals 0, and this is what you are getting, this relationship. Let us discuss how we can compute depth under pure translation. Consider these two cameras in the stereo setup. As we have already mentioned that we have the corresponding camera matrices P and P prime, and where P is given by the K calibration matrix into identity and 0 translation, which means the center of the first camera would be at in the origin, and also this translation between these two cameras, it is given by a horizontal translation T x 0 0, that is the pure translations we are considering, and there is also no rotation. So, in the horizontal direction it is a pure translation, and there is no rotation matrix R. As we can see in the case of second camera matrix, here we have same identity submatrix here in this part instead of a rotation matrix, or you can say rotation equal to the identity matrix, which means no rotation, and this is the translation part. And this is a second camera whose calibration matrix is also different, which is K prime, and our objective is that to compute the depth here. So, in this case, since it is a canonical form, so your principal plane is also the xy plane of the coordinate system in the first camera's camera centric coordinate system. So, this is your canonical form. So, this is the z directions if I consider. So, your depth will be the z coordinate in this case. So, let us see how we can compute this z considering the corresponding points x and x prime in the stereo view. Now, the camera center of the second camera, it should be minus T x 0 0. As you can see that translation T in this form will give this particular form, because as we know that the camera center C prime, I am using tilde to denote that it should be expressed in world coordinate. So, that should be minus r, I mean T equal to minus r r C tilde, that is T, and so in this case we can say that, so you can write here T equal to minus r C prime tilde, where r is your equal to I, r equal to I rotation matrix. So, C tilde can be written as also minus T. So, which will give you minus T x 0 0, that is the camera center in this form, in this kind of configuration. And then we can compute the corresponding world coordinate of the scene point. So, here scene point is x, and in our convention when I am using the world coordinate in non-homogeneous coordinate convention, I will be using tilde on top of it. So, as you can see that what we have done here, we have expressed the the image coordinate x into the normalized canonical form, that is k inverse x, which means the distance of image plane from the camera centric coordinate system is 1. So, in that case, if I multiply with this the value z, that itself will give me the corresponding scene point at depth z. So, that is how this expression comes. Similarly, if I consider the other camera, there also we can use the same convention, but since there is a translation involved here. So, the coordinate will be x prime plus t, and again it is the same form. It is because here also there is no rotation. So, your depth, your principal plane is also the same x y plane, and you can use z coordinate as the corresponding depth. So, z and k prime inverse x prime will give you the relationship, will give you this coordinate under this camera centric coordinate system. Under this camera, this should be this should give you that particular thing. So, now if I consider k equals k prime, that means two camera have the same calibration matrix, then this relationship can be further simplified. It takes a very simple form, and as we can see from here itself, if we subtract this equation, if you subtract say this equation from this one, then you will get this relationship. That means you get z k inverse into x prime minus x, that should be equal to t. That is how we will get, and from there we can get x prime, that means the second image coordinate of the scene point in the second camera, that should be equal to x plus k t by z. So, this is the relationship between x and x prime. So, there is a shift in the horizontal direction, and the amount of shift is determined given by this k t by z, and from there, from this shift you can determine the depth z as k t by x prime minus x. So, this is how we can compute depth, and this relationship can be further simplified once we take the take a simple form of k. So, where in the calibration matrix we consider only focal length is the parameter, and all other parameters they are initialized to 0, which means principal point is also the center of the image coordinates. There is no skew, and under this situation you have a very simple calibration matrix. So, this relationship, that means z equals k t by x prime minus x, and where t is also given by this column vector. So, that would be simplified as z equals f t x x prime minus x. So, this is one of the familiar equations of computing depth in a stereo setup, where optical axis is parallel between two cameras, and also both the camera have the same focal length, they have same identical calibration matrix, and the shift between these two camera is t x. Then we compute depth. Incidentally, this value x prime minus x, which is the shift of the corresponding point along horizontal direction, or this is the x coordinates. These are all scalar x coordinates. You should note here once again that here this x and this x prime, it denotes the vector, whereas finally in this computation, when we have considered x prime minus x, this is the scalar x coordinate of those 2 points. So, this is also called disparity. So, in a stereo setup we can compute this shift or disparity, and f and t x could be the parameter of the stereo imaging system. So, only using image computations over those stereo images, you need to compute disparity at every point, and that is how you can obtain the depth. This could be further generalized when we have a general configuration or arbitrary configuration of two cameras. Instead of having a parallel stereo configuration, let us consider that you have a general projection matrix for the second camera, whereas the first camera is the reference camera, and there we follow the same canonical structure with a calibration matrix K. And in the second camera, we have this general structure where you have the calibration matrix K prime, which is a different camera. It could have different focal length, etc., and it has rotation and translation parameters as well, which means they are not separated by simple horizontal motions. C prime or the center of the camera is rotated and translated with respect to C. It has a general configuration. So, under this situation, how we can compute this depth that we would like to discuss. Now, there is a very simple way by which you can map this problem to a parallel stereo problem and use the previous relationships what we derived here itself. So, what we can do? We can consider that let there be another imaginary camera which has the same center C, but it is related by only rotation with the same rotation matrix R. And then we can compute the homography between these two image planes. We know that it establishes a homography, we have already discussed in two dimensional perspective projection during projective transformation also, and we will also see how this homography also could be obtained. We can also find out here itself. So, once we have these things, for example, you consider originally you have 2 points, say x, this is the reference camera. So, we will be considering this is x and another point, say x prime. So, these are the say 2 corresponding point of the scene. Now, due to rotational homography, we bring x to the new imaginary camera setup, where we will be considering this point is x 2. Now, these two, since we have exactly applied the same rotational matrix R, now this image plane and this image plane, they have the parallel stereo configuration. So, now we can apply the parallel stereo results under this scene. That means, what we need to do, we need to consider now the corresponding points under this 2 camera setups as x 2 and x prime, and use this corresponding pair of corresponding points to compute the depth. So, let us elaborate these computations further. So, let us first compute the rotational homography in this case. So, assume that you have the second camera. Let me rub this thing just to make it more clear. So, consider that the second camera matrix as P 2, that is the imaginary camera as I mentioned, which we considered whose image plane should be parallel to the image plane of P prime after performing these rotational transformations on the image planes. So, P 2 since it is related with the original reference camera by the rotational matrix R, and also we would like to have the same calibration matrix of the second camera K prime. So, the projection matrix of P 2 is given in this way, that it has a calibration matrix K prime and then parameter of rotational matrix R, and the center is still at origin 0, and that is the same as the reference camera. So, under this configuration, what should be the homography between these two scenes? So, here we can see that x 2 can be written as in this case it is the image of the same scene point x. So, this could be written as k prime. So, this is k prime, which is not very visible from this part. So, k prime r 0. So, this projection matrix P 2 into x, that is what is x 2. Further simplifying it. So, this is x 2, and once again we can simplify it in this form, which means I can take r outside. So, it becomes k prime r I 0 x. Now, this part can be expanded into this way. So, our objective is that out of this I will be taking this part here, and then k I 0 x can be considered as x, small x, that is the original scene point. So, once again this is x, this is x, this is x 2, which is mapped by homography H, and then x prime. So, originally x and x prime is the corresponding points, and now it has become x 2 and x prime is the corresponding point. So, now the relationship between x 2 and x is given in this form. So, the rotational homography under this situation, it will become k prime r k inverse. So, this is a rotational homography. So, this is a rotational homography. So, once you have obtained this, now you can apply the stereo results between x 2 and x prime, which means that I can write x prime as x 2 plus k prime t by z. Use the previous result, where it was x 2 was earlier x and this was k, but now calibration matrix of these two setup, it is now k prime. So, it is x 2 plus k prime t by z. So, again if I use the homography relationship between x and x 2, it would be k prime r k inverse x plus k prime t by z. So, that is how x prime and x is related. Now, it is a simple mathematical manipulations, algebraic manipulation. So, I can bring k this side x prime and then divided by k prime, then z should be equal to k prime transpose by x prime minus k prime r k inverse x. So, from here we can get this relationship. So, in this way we can obtain the depth or z coordinate under this situation of the scene of this kind of arbitrary general motion of camera. So, let us work out a problem to understand these relationships, that how the depth could be computed or z coordinate could be computed. You consider a stereo setup with these projection matrices P and P prime, which are given here as it is shown. And now, what you need to find out that you have been given two image coordinates, 3D points are there, 6, 8 and 9.338 in left and right cameras. So, you should note that we have already satisfied that constraint of keeping the y coordinate same, because that is what we discussed as a property of this particular scenario. You can find out that the component of submatrix M, they remain the same, and only this column vector they are different. So, which means it is a case of cameras which are related with only translations of origins, because you know that this is given by minus M inverse this column vector, this is given by minus M inverse this column vector, and that is the only thing, because others are either rotations or rotation etcetera. There is no rotation, relative rotation between these two system. So, this is a case of pure translation. So, in the under this case, we already have seen that your y coordinates of the corresponding point, they should remain same, because there is a special case of, it is a special case of stereo, and the fundamental matrix is given by simply by E prime cross, as we have seen earlier also. So, now let us compute the depth of this particular no, in the particular scene, what should be the depth of the scene point. So, this is the scenario. Your P is given as k I 0 and P prime is given as k I t, where k is given in this form 6 0 0 0 0 6 0. So, this is what is k and this is what is t. So, you note that t needs to be scaled by the value 6, because in the previous case it was k t, in the representation it is k t. So, you will get if I multiply this one, then only you will get the previous matrix. So, x prime is equal to x plus k t by z, and so the z equal to 6 into 10 by 6 by x prime minus x. So, this is what that is what we will get from this expression. So, which is equal to 3. So, with this let me stop my lecture here, and we will continue this discussion in my next lecture. Thank you very much.